All right, so this is just the continuation of that last problem in my first green theorem video that kind of ran out of time here. So we were talking about how if we want to show that the line integral of f dot dr is 2 pi for every positively oriented simple closed path given this f here, this is one way that we could set it up. So we can think of this as infinitesimally small, okay, just circle, an actual circle. And what we're going to do is we're going to cut the region and kind of do a sum of two line integrals. So we're going to do, arbitrary path out here. That's my c. And then I'm going to go minus c prime. And if I add them together, I can basically get the whole region d, right? So if I add them together, I'll get all of d. So I can really just work with now this double integral, all right? And so now I'll just go and start plugging things in. And so partial of q with respect to x, okay? Q is x over x squared plus y squared. So it's going to be derivative of the top, which is like 1 times the bottom, and then minus derivative of the bottom, which is minus 2x, just times the derivative of the top, which is x, right? Then all over the bottom squared. Right? And if you look in here, you're going to get x squared minus 2x squared, right? So you're going to get a minus x squared. And if you do the minus partial of p with respect to y, you're actually going to notice that you're going to get the same thing. You're going to get y squared minus x squared over x squared plus y squared squared. And so if you look at this, okay, so this is partial of q with respect to x, this is partial of p with respect to y. If you look at the top, right, you're going to get y squared minus, if you combine these, right, minus x squared. So this is actually really nice because these will cancel out. And that means that this double integral is 0, okay, which would then imply, right, that the line integral around arbitrary path of like p dx plus q dy is going to equal like it equals this thing, right? Because like this plus this is 0, so it must equal like the negative of this, I guess, right? And so if it equals the negative of it, right, I could just change the negative with the minus sign right here. So instead of going this way around it, I'm actually now going to go back to counterclockwise like that. And so this line integral is going to equal the negative of this one. So I'm just going to do the negative by doing c prime. That's like the circle in now the counterclockwise orientation. If you can't tell already, orientation is super important in this stuff. And so, these two line integrals are the same. So what I would do is I would just work with the easy one, right? This one is definitely the easy one. That's because that's like the circle, right? And so if we wanted to parameterize the circle, right, we could just do x equals a sine t. Nope, sorry, a cos t. Should really know my unit circle by now. And then y is a sine t. And so, a here is just thought of as the radius. And a is like infinitesimally small, right? That's the idea because of the singularity. You got to kind of not include that origin right there. So now you can go and actually do out this line integral. So we're just going to basically do, the line integral from, we want to go 0 to 2 pi because we want to go full circle. And then we're just going to do f of r of t, and then we dot that with r prime of t dt. This is just my normal like line integral, right? And so if I do all that out, let's see, I think I can squeeze it in here, 0 to 2 pi, and then I would just, so I'm going to, plug these in here, right? And then I'm going to dot it with the derivative of this, and it's just a lot of crunching stuff. So I'm just going to go and write down what you would get. So that is what you would get if you do f of r of t, so put these in, for x and y, then you dot that result, that composition basically with the derivative of this, right? And then if you look at this, actually a ton of stuff is going to cancel. You're going to get a squared sine squared here. You're going to get a squared cos squared here, right? You have a squared cos squared plus a squared sine squared. All of that goes away. Super nice. All of that goes to 1. And so now you're doing 0 to 2 pi, really just 1, dt. And of course, that is just the length of that interval, which is 2 pi. So pretty tricky problem. Lots of conceptual steps there to get to this point. But basically, what we've done, just kind of recap, is we took an arbitrarily small circle. A is just thought of to be basically 0. And C is an arbitrary path around encloses the origin. And we were talking about how we could add together these two to get the whole region D, whatever that region D looks like. Then we took our partials. This is greens, right? Then we took our partials. We get this. And we saw that double integral should be 0, right? Which meant that these two line integrals should be, this should equal the negative of this or vice versa, right? Which I handled by just changing the negative sign in there, right? And then now we just computed the easier one of these two things in yellow, which was the one around the circle, because we know how to parameterize that. And so then you just go through all that, and you get 2 pi. So that does it. So that shows that no matter what, for this vector field, no matter what what path, you pick that is a simple closed path around the origin, it will always equal 2 pi for that, which is very nice.